Ok, a gente está ao vivo. Hello, everyone, and welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the honor of having Dr. Chies Santos, a professor at the Federal University of Rio Grande do Sul. Dr. Santos is an observational astrophysicist focusing on understanding how galaxies form and evolve. Her research group focuses mostly on extragalactic archaeology and the transformation of galaxies, planetary nebula, galaxy clusters, star formation, as well as active galactic nuclei. Today, her topic will be on globular cluster systems. Dr. Santos, thank you very much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
Thank you, Tassia, for the introduction and invitation. So I will present the seminar in English, but if students feel more comfortable to ask questions in Portuguese, please do that. So I was supposed to give this seminar back in mid-October, and on the beginning of the week, the seminar was scheduled. I tested positive for COVID. And I thought it was going to be light, and I was happy to try to give the talk that week anyway, but it turned out to be pretty nasty, including complete voice loss. So I'm glad Tassia suggested to transfer. Anyway, happy that this time it's finally working out. So the title of my talk is Globular Cluster Systems as Probes of the Buildup of Galaxies and Their Environment. And this is my research group at the Physics Institute of URGS, named Extragalactic Archaeology and Transformation of Galaxies Group, or EAT for short. Here are some of the faces in the research group. Part of the group focuses on understanding the transformation of galaxies, especially finding and characterizing jellyfish galaxies. This is subject of a future seminar. So one of our lines of research focuses on using globular clusters to understand galaxy formation and evolution from the Milky Way to galaxies at around comma distances for now. And here are the grad students that work on this topic. And here are the hardworking undergrads. And I highlight that for this line of research, we work a lot with co-supervision with my colleagues Charles Bonato and Cristina Furlaneto. So for this talk, I'll give a long introduction to the field of globular clusters, starting from the Milky Way and local group galaxies. Then I will review the main properties of GC systems across a range of masses and environment, and add in some of our own past work. So I'll move on to present recent works from our group on the topic of GCs, specifically on the nearby triplet of spiral galaxies M81, and on low surface brightness galaxies we found recently. So starting with galaxies. So today we have a pretty good idea of how galaxies are formed. We know the galaxies formed hierarchically. We start from this cosmic web of rotating dark matter halos, and disks form in these dark matter halos from cooling gas. If mergers between these kinds of galaxies happen, we might create spheroids. If more mergers may occur, new disks can grow around the spheroid if further gas cools. And here is a well-known simulation. Here's a well-known simulation. What is wrong here? Well-known simulations showing the assembly of a galaxy in this context, in this cartoon context I just introduced. And at the core of this hierarchical growth paradigm is the agglomeration of mass in galaxies by mergers or accretion. And how can we reconstruct the assembly histories in the outskirts of galaxies? As these assembly histories that bring up these structures, such as these ones seen in this beautiful, very deep image of a nearby elliptical galaxy. So how can we determine the fate of a galaxy? As stars, dark matter, gas, they all scramble up and erase the traces of the progenitors and of the processes that occurred prior to and during the event. And objects caught in the act of merging and just after a burst of star formation are rare in the local universe, and we have to be often guided by simulations. So we need to go out there and look for a population of objects within galaxies and their environments that can help us testify to the combination of different progenitors and to any new star formation that might have occurred as part of this growth process. And these are the globular clusters that are present in most galaxies. So GCs are old stellar populations with ages reaching the ages of the universe, held together by gravity. And here is one such object from our Milky Way named M15, which we worked quite a lot on. GCs are bright. They contain around 10 to the 5 stars. They're ubiquitous in most galaxies, and their formation accompanies major star formation episodes in their host galaxies. GCs when seen at distant galaxies like this highlighted in the halo of one elliptical galaxy to the right are like lighthouses that allow us to study the outskirts of galaxies at great distances. As mentioned before, globular clusters are present in most galaxies, but in different quantities. So in dwarf galaxies, we have from no globular clusters to tens of these objects, in ellipticals from hundreds to thousands, and in spirals like our Milky Way or our neighbor Andromeda, from tens to several hundred. We could perhaps say that the field of globular clusters can be divided into two, the field of resolved GCs and unresolved GCs. For resolved globular clusters, we can resolve and study the individual cluster stars and measure their properties either through photometry or spectroscopy. And for unresolved GCs, we study the integrated light of the cluster as a sum of all the stars in the cluster. And then we derive integrated colors, integrated spectra, and make use a lot of stellar population models. The first obvious system to look for GCs is the Milky Way. And GCs in the Milky Way are typically found in the spheroidal components of our galaxy, the bulge and the halo. And here in the top panel, in blue, we have the distribution on the sky of the globular clusters, and in red of the dwarf galaxies as viewed by the Gaia satellite. In the bottom panel, we have these same satellites and the predicted pathways from Gaia's proper motions measured for GCs over the next 10 million years, and for the dwarf galaxies over the next 100 million years. And over here, I highlight the location of two GCs, one that is metal rich, NGC 6528, and the other that is metal poor, M15. In the Milky Way, the metallicity distribution of GCs looks more or less like this, a bimodal distribution with a peak of metal poor objects and a peak of metal rich globulars, and a few objects of intermediate metallicity. And what about their ages? They are older than 10 billion years. And how do we measure their ages and metallicity content? Well, we take spectra and images of different colors. For instance, here we have 3 objects, one that is metal rich, one that is metal poor, and another of intermediate metallicity and age. They have absorption lines that are slightly different. And over here, I highlight the location of the large and small Magellanic Clouds. And zooming in, the SMC and LMC have a few old globular clusters, some of intermediate age, and some that are just a few million years old. So let's check it out. Here we have a metal poor, an old GC in the larger galaxy, and a metal rich and intermediate age in the smaller galaxy. In the same field, there is also a very famous GC from our galaxy, 47 Tuc, that is old and metal-rich. The clouds also host many other star clusters that are much younger, such as the Taranta Nebula and these other guys over here, that are not regarded as globular clusters per se. In other late-type galaxies, such as our spiral neighbor Andromeda, besides being found in the bulge and the halo, globular clusters are also found heavily associated to streams, like these here. In the most massive galaxies, such as these two at the center of the Hydra cluster, they have an estimated number of 15,000 GCs per galaxy, like this little dot inside the white circle, that can be seen with very deep imaging. GCs are not only found in the bodies of their host galaxies, but also free-floating in galaxy clusters, not necessarily bound to a host galaxy. So the Virgo, the Fornax, the Coma, and the Abell 1689 galaxy cluster, like this one in the slide, all appear to have rich populations of intra-cluster globular clusters. This beautiful super deep HSD image estimated around 200,000 GCs in this single deep HSD field. When the first image of the new JWST was released, it was very impressive to see so many little sources in the center of the SMAX 273 cluster at redshift 0.4 that I did stop all the work I was doing that day. You can see in this region over here, lots of little sources. I did post it on Twitter, although I had only 4 likes. And later on, the first archive preprints came claiming the detection and first analysis of globular clusters and ultra-compact dwarfs in this image, although these papers are still under review. And in this side image, you can see the GC candidates highlighted here in green, or the SMAX 723 famous picture from JWST. Now a bit of context on galaxies and their GCs. Let's have a look at simulations, observations, and scaling relations. So cosmological simulations of galaxy formation, at least for massive galaxies, appear to show a two-phase character with a rapid early phase at redshifts greater than 2, during which in situ stars are formed within the galaxy from infalling cold gas. Then we have an extended phase that happens since redshifts of about 3, during which ex situ stars are primarily accreted. In this later phase, massive systems grow a lot in mass and radius by accreting smaller satellite systems formed at quite early times, outside of the virial radius of the central star-forming galaxy. And one known result from galaxy evolution is that massive galaxies show a substantial size evolution since about redshifts of 3. Here we have the size evolution of massive galaxies versus redshift for both spheroidal and disk-like objects. And we see that spheroidal galaxies seem to undergo the most growth. And here's a cartoon picture for the formation of early type galaxies with this two-phase formation. We have a first phase, generally called and found in the literature as the red nugget phase that happens at high redshift, followed by a second phase that happened in the last 8 billion years, dominated by dry mergers, where we form these beautiful streamy structures around these galaxies. And if we let it coalesce, we might observe the massive galaxies that we see in the nearby universe today. And it is possible, however, to find galaxies in the local universe that have not gone through this second phase, and are like time capsules of this higher redshift universe. And these objects are commonly found in the literature as relics. And our group has done some work on this front, both on simulations and observations, to find these galaxies and try to characterize their GC systems. And how do we add these GCs to this picture of two-phase galaxy formation? So we have that in optical colors, we generally see this bimodal distribution, for instance, in G minus Z. And in this picture, the red metal-rich GCs would form in this first in situ phase, whereas the second phase would bring in the blue metal-poor population of clusters through minor mergers. And if we look at the age metallicity relations for Milky Way globulars, we have that the metal-poor GCs over here may have been accreted from neighboring dwarfs because they tend to follow the age metallicity relations for the SMC and LMC, for instance, while the more metal-rich GCs, the bulge GCs in this green region, tend to have different age metallicity relations. And cosmological simulations tell us that cluster formation happens in a turbulent environment at higher Z. And here I show examples of the state-of-the-art simulations, such as e-mosaics that is paired with EAGLE, the fire simulation, and other semi-analytical simulations paired with Illustrate. Although substantial advancement has been achieved in the past years, we expect much progress in this front in the upcoming years. And here we have a video of one of the e-mosaic simulations showing the formation of a Milky Way-like galaxy. The gray shading shows gas fragmenting, forming stars and falling onto the central galaxy. And we have newborn stars blowing up bubbles into the gas with their intense radiation and supernovae explosion. The GCs are indicated by color dots, where the color indicates the chemical composition. Blue clusters have a low level of elements, more massive than helium, whereas red clusters have a high level of such elements. Over time, the merging of the central galaxy with the smaller satellites brings in a large number of globular clusters. And these simulations show that the GC formation peaked at redshifts of about 2 in a similar manner to the star formation histories of galaxies. And observationally, we see that the ages of clusters are mostly older than 10 billion years. And this has been determined through careful analysis of spectra and images of different colors. And you might be wondering how images of different colors and spectroscopy work to measure these ages and metallicity. So ideally, we would like to have spectra for each object we study. With spectra, we can measure the strengths of different lines and compare to stellar population models. But spectroscopy is observationally very expensive, and imaging costs less. And with less observational time invested, we get colors of several objects in one go. And here I show a spectra for one extragalactic GC from a recent paper. And all these colors represent images of different filters from one given survey. And by having images in several bands, we can build a spectral energy distribution. And by fitting the SED, we can then infer the properties of the objects. If we have less bands, less images, we can use color diagrams, such as these ones, to the right, and still have some constraint on the ages and metallicities of these studied objects. This is what I did in the past. And then models for GC formation, such as e-mosaics that I shown before, they predict that spiral galaxies, where GCs are less studied, should have a broad range in GC ages, as can be seen in these age metallicity relations shown here for redshift 0. Here we can see a wide variety of age metallicity distributions, which arise due to differences in the formation and assembly histories of the host galaxies. And this is yet to be confirmed observationally. If we look at the GC system's color distributions for different luminosity host galaxies, we have that the lower luminosity galaxies have almost exclusively blue metal poor GCs, whereas the color or metallicities of both red and blue peaks correlate with host galaxy luminosity. And dwarf galaxies, metal poor globular clusters, tend to be more metal poor than the metal poor GCs of more massive galaxies. And color-color relations, such as these ones, G minus R versus I minus Z, have been reported to vary according to the location in the Virgo cluster. So from the center in red to the outskirts in blue-violet, we have the Milky Way GC relation, these ones in black here. They seem to be closer to GCs in early type galaxies that are far from the center of the Virgo cluster. So there seems to be an environmental effect going on here. And this was the subject of a PhD thesis of the group. Another interesting scaling relation is the number of globular clusters normalized for a host galaxy luminosity, MV of minus 15. The specific frequency, Sn, seems to be high in both giants and dwarfs, but seems to be universally low at intermediate luminosity galaxies. So coming back to the relic galaxies I was talking about before, which are massive, compact red galaxies and displayed old stellar populations. These three relic galaxies fall well below the mass size relation for local galaxies, this blue line. And in contrast to Virgo GC systems of host galaxies of similar mass, this prototype relic NGC 1277 appears to contain almost exclusively red globular clusters. This green histogram is for ACS Virgo cluster survey galaxies at the same mass bin, while the green one, the orange one, is for NGC 1277. And together with Carla alum, a former postdoc here in Porto Alegre, we analyzed the GC systems of 14 relic galaxies with archival HST I and H band imaging. And these galaxies are all found to be outliers of this redshift 0 mass size relation. In fact, most of them fit much better with higher Z mass size relation curves. In this work, we try to quantify the richness of these GC populations through the specific frequency parameter, Sn. And in this figure shown here, we have the specific frequency parameter versus the host galaxy absolute magnitude in the V band for our sample, and a compilation of galaxies from the literature, which comprises a sample of around 400 ETGs, early type galaxies. And the dashed cyan lines will represent theoretical predictions, assuming a fixed GC formation efficiency per total halo mass. And we find low values of specific frequency for our sample, less than 2.5, with a median of 1. We can also compare the total mass of a globular cluster system with its parent galaxy mass. Here we have that the GC systems are connected to the properties of their host galaxies and show a direct relation with the dark matter halo of their parent galaxy. And this is still to be verified for lower mass halos. Also, there's an empirical relation that is more and more appearing in the literature regarding the number of globular clusters and the total mass of the host galaxy. So here by total mass, I mean the stellar and dark matter masses together. Thus, by counting globular clusters, we can determine a lower limit to the total mass of a host of a galaxy. And if we have other ways to measure the stellar mass, for instance, we may well determine a lower limit to the dark matter fraction. And to calculate the number of GCs. We use the globular cluster luminosity function, the GCLF, which is defined as the relative number of GCs per magnitude, and we can use it to determine distance. The GCLF from the Milky Way has a turnover magnitude close to the V band magnitude equal to -7.4, and seems to be universal. And the shape of this GCLF is very close to a classical Gaussian. So to estimate the number of GCs from a galaxy, we fit the GCLF to the magnitude distribution of the clusters. And here are examples of GCLFs in the local group, the Fornax cluster and the Hydra cluster. So as we increase the distance, we sample less and less the faint end of the GCLF. And now I'll show some recent works and ongoing works on one nearby triplet of spiral galaxies and another on a sample of low surface brightness dwarf galaxies. Starting with this that is now published within the J+ collaboration, the largest compilation of globular clusters in the M81 group of galaxies. So in this project, we studied the M81 group of galaxies at 3.6 megaparsecs, where we have these three main galaxies, M81, M82, and NGC 3077. In the left panel here, I show the H1 maps of this system overlaid on top of a J+ composite image we created. This system is a beautiful mess, and our goal here was to look for GC candidates around this field of view. So J+ is a survey precursor of JPAS in the north of Spain that is undertaking data in 12 bands, these ones over here. And the filters have been chosen to probe key stellar spectral features. And in this recent work, we report on a list of GC candidates. We start by performing photometry ourselves because the Normals extractor survey photometry will miss the clusters, especially closer to the galaxies. And also we make use of Gaia proper motions. So we start from a literature sample of 105 spectroscopically confirmed GCs. We developed a customized statistical model to search for new GC candidates that accounts for missing data and photometric errors. And we search for objects that look like GCs on the set space via principal component analysis, taking into account uncertainty. And in a search in a region of around 3.5 square degrees, we expand the current list of known GCs by quite a bit. We started with 7.2 thousand point-like sources with photometry in 11 filters and 105 spectroscopically confirmed GCs, and arrived at 640 new GC candidates shown here in this middle panel. And in the right panel, we have the galactocentric distance versus the G-I color for the literature confirmed GCs, and the GC candidates separated by their proper motion value. The takeaway message from this analysis is that the confirmed GCs from the literature are in the range of intermediate to blue, and the candidates with lower proper motion, the orange markers, they seem to follow the same trend. And this is compatible with these objects being halo and intra-cluster globular clusters, or intra-group globular clusters. And we also seem to see an overdensity of candidates connecting M81 and M82, and an absence of clusters towards the south of M81 in the opposite direction to M82. We also don't seem to recover candidates close to NGC 3077. And this is because we think the training sample, the training sample is for globular clusters, and this galaxy is an irregular one, and then has a lot of young clusters, and the sets are different. So we look at a few example color diagrams and color distribution. Map the metallicity distribution function of the known spectroscopically confirmed GCs to the GC candidates ones, and study their spectral energy distributions, and they seem to be compatible with that of globular clusters. And we have already a few spectra have been taken on Gemini with poor weather in Hawaii, in the northern one, and we have more proposals under review. So this is work in progress. And the last one work I want to mention is on the GC populations and upper mass limits for low surface brightness satellites around their closest S0 and GC 3115, where the globular cluster part of this paper we are currently finishing was largely done by the ISE student Marco Canosa, the undergrad student. And looking to study low surface brightness galaxies in low density environments, our group obtained deep imaging from Blanco DCAM back in 2017. And this region around NGC 3115 is a low density environment with not many massive neighbors around. And our first step was to inspect the area and search for ultra diffuse galaxies and low surface brightness dwarf candidates. So we performed visual inspection and reached about 40 low surface brightness candidates in these two DCAM fields. And after the photometry, we obtained the structural parameters for these 40 objects and found that 24 were consistent with being low surface brightness dwarfs around NGC 3115. In this left panel, you can see the distribution on the sky of our candidate LSBDs. And while inspecting the residual image of our LSBD candidates, we noticed that several of them presented point sources that could be globular cluster candidates. And here are the Blanco images. And we followed them up with 6 Gemini GMOS pointies, shown as magenta squares in this left panel. And on the right panel, I showed the 9 LSBDs for which we obtained GMOS imaging. And after selection of GC candidates, we fit the globular cluster luminosity function, which I defined in the introduction part of the talk. And the shape, so to estimate the number of GCs, Marco used the MCMC to obtain the mean value and the sigma and the amplitude from the distribution of the number of GCs as a function of magnitude. And now that we have the GCLF from each low surface brightness dwarf candidate, we can recover the number of GCs from each galaxy. We consider, based in the works from the literature, that LSBDs with numbers of GCs less than 1 are consistent with not having any globular cluster. So in this first plot, I show the number of GCs versus their magnitude in the B band compared with other works. The point from Sharina et al. Represents a previously well-known studied dwarf that was studied with HS. And the points follow the distribution from the Fornax cluster that are low surface brightness galaxies, except for point 1. And for this point, which is LSBD, that we call 22. And this is because this galaxy, this LSBD, which is shown here, the image subtracted one, the galaxy subtracted one, is very close to a massive galaxy at 70 megaparsec. So having deep imaging, we get the halo clusters of this galaxy, and we contaminate the GC system of the dwarf. And in this other plot to the right, I show the specific frequency versus the magnitude in the V band that we obtain. These 2 points here are the ones for LSPD 22 that have a lot of contamination. And the other one is for LSPD that the GCLF model didn't fit very well because of the low number of candidates. And the other points also follows the ones from the Fornax previous study. And arriving to the end of this part, this is the take home point. By using a number of GCs, we may also recover the upper mass limit for these low surface brightness dwarfs around the GC 3115. And this results that we agree with the ones for the Fornax cluster. And the LSPD's total masses vary from 10 to 10.6 solar mass. Now, let me quickly mention these prospects with upcoming facilities, both from space and from the ground. These are facilities to keep an eye on for this kind of work. Of course, I'll be biased to ones that I'm working on. So for this audience, I suppose I don't have to introduce the Rubin Observatory, but these 6 super deep filters will be amazing for this kind of study. And also the more modest JPass is also very good because we will have several key spectral features with narrow bands where we can observe the more nearby systems. And the space facilities I highlight here are Euclid, CSST, and Roman. Euclid is from ESA and Roman from NASA. CSST is the Chinese Space Station Telescope. Euclid and Roman are in the near infrared and CSST in the optical and UV. And talking humanity-wise, CSST will be a substitute for the Hubble Space Telescope, and Euclid and CSST are expected to be launched in the next couple of years. Euclid was severely affected by the Russian-Ukraine war, as it was going to be launched with a rocket from Russia, but a few weeks ago, according to ESA's Twitter, they have set an agreement with SpaceX to launch Euclid. And to have an idea, here is the field of view of CSST. Euclid and Roman W first, compared to HSTs in yellow and orange. And this will be a huge step in efficiency for observations from space. And last but not least, here are the limiting magnitudes these surveys will reach, with LSST being the deepest. And the Chinese Space Station Telescope will be a bit shallower in some of the similar bands, but from space with a better spatial resolution, reaching 0.05 arcsecond per pixel in one of the cameras. Thus, we will be able to probe the near complete GC systems of galaxies out to redshifts of 0.05 from all morphologies and environments. That's about 200 megaparsecs. So I hope I have convinced you that globular clusters are powerful probes to understand the evolution of galaxies, including dark matter in galaxies. And here I presented some of our group's work on GCs in relic galaxies, in the M81 triplet, and in low surface brightness dwarfs, and showed that the present and near future are photometric surveys that will give us a near complete picture of GC systems out to 200 megaparsecs for different galaxy morphology and environment. Thank you.
Thank you so much, Dr. Santos, for the very interesting talk. We now have time for questions from the audience. If you're on YouTube, you can put your question in the chat, and I'll read it out to our speaker. Go ahead, Reinaldo.
Yeah, okay. Anna, I have two questions, and my first one is about the three types of metallicity spectra that you showed at the beginning of our talk. The reason is that we have been using techniques, in special one that we call gradient pattern analysis in the deep learning issue to classify supernova from spectra. Okay, and it works very well when we have balanced samples for the different types. So how many good quality samples are there for the spectra of globular clusters discriminating the three spectral patterns of metallicity? It is a balanced data. I mean, are the three types of subsamples well represented? You know?
So I would say they're mostly these, if you go for galaxies at the distance of Virgo fornax, you'll find a lot of old and metal poor and some old and metal rich. I would say they're quite balanced if you go to a big, massive galaxy. But you're going to find more of these in the dwarfs.
Okay.
But I would say that you could use the photometry, like the multi-band photometry. Can you use this for this kind of analysis you're mentioning? Okay. Or you need a real spectra? That's my question to you.
We can use both. We can use both, but we got more good results from the spectra, you know. But we have tardies for supernova that are synthetic spectra. So that's the question also important. Are there synthetic data for the simulation spectra for globular clusters?
Not that I'm aware of. There, like for the optical, you mean, or which wavelength would you need?
No, I mean for the three types of spectra that.
Yeah. Okay.
Can you do simulations for that? Oh, okay.
Yeah, you can use. Yeah, you can for sure.
Okay. I have also a more theoretical question, more theoretical doubt. What's the role of the turbulence in the dissipative phase compared to the accretion one? I ask this because, you know, it must be a very good example of non-homogeneous turbulence for fundamental physics. I have been working a lot on that, you know, but I'm not specialist in globular clusters. That's why I'm asking you.
You mean in the formation, in their assembly process?
Because you mentioned that there is the dissipative phase comparing to the accretion one, right? And I believe that in the dissipative one, the gravitational instability and of course the turbulence is very important in this phase. Can you comment something about this?
Let me think. So you mean compared the role of turbulence in the accretion versus the first phase when I talked about the galaxy,
right.
Galaxy formation.
You mentioned dissipative process, right? And I believe.
Yeah, so this first one.
Right.
Yeah.
But you didn't mention what kind of dissipative process. That's why I'm asking you about turbulence.
So I would have to go back and check in the simulations, which I'm not really doing that. We just use the simulation. So I don't know how to answer your question. But I would say that we can have a look at what is being done with the, like for instance, the E-mosaic simulation.
Fine. Okay.
But they use Eagle, so they put the clusters like they do a zoom in. But we can talk later.
Okay. Thank you.
Are there any other questions? If so, just reminding everyone, as Ana said, if you guys want to ask questions in Portuguese, that's fine too. If you're shy or you're having some audio problems, you can also put your question in the chat and I'll be happy to read it out.
And I'm happy to answer questions through email as well.
Okay. I have a few questions if I can go ahead. Now I have to, okay, there was a slide where you were showing a 600 and something. Okay, Guilherme, just 1 moment, and I'll let you ask. So like you were showing the confirmed globular clusters. Can you, like there were 600 and something, 40 something.
The M81 one. Okay.
Mhm.
Let me find here. Okay, here.
Yeah. So the conference, yeah, 640. That was close.
So we only had these guys here that had the spectra previously observed that we used like a training sample.
And then on the other plot, so I see like a lot of dots, and if I look at the labels here, there's GC candidates. So what are the other dots exactly? Those were not confirmed as globular.
Yeah, so
is that it?
So these are we separated by Gaia proper motions. So some of them didn't have Gaia proper motions, and the other ones had. And I don't have it's in the paper, but we looked at the distribution of these guys in proper motion phase, and some they mostly were the orange ones, but some of them were greater than this value here. So we are not very sure about if they're really confirmed candidates. That's why we need spectroscopy. So we are following them up with Gemini.
Thanks. Guilherme, go ahead.
Hi, Anna. So
Hi.
the question, you kind of touched upon the question that I had. First of all, nice work. I really like this topic of extragalactic globular clusters. So the question that I was going to ask, one of them was about your Gaia, your usage of Gaia proper motions in your selection, because I think how bright are these globular clusters? Like, what are the magnitudes in Gaia? Because I mean, what is the quality of the astrometry from Gaia for these globular clusters?
It's not amazing. It goes to the limit. So in our band, 19,
I see.
20.
Yeah, it's right, reaching the faint limit of Gaia.
The limit, yeah.
I see, but do you utilize any of the astrometric quality cuts that Gaia recommends, or you can't even use those because they are so faint?
Yeah, we can't use those.
I see. And the other question that I had was about, you talked about the masses of galaxies that you analyze using, that you detect globular clusters in. And what I was going to ask is, when you talk about the mass of a galaxy, you're talking about the stellar mass, and the other question is related to that is, when you infer the mass, you're using like the scaling relation with globular clusters, or are you talking about dynamical masses?
Yeah, so I was talking about the total mass, so the stellar mass and the dark matter mass together.
But basically, you find the stellar mass using the scaling relation. How is that?
The total mass. So we cannot disentangle. We would need another way to get the stellar mass.
So you don't use any scalar relation. You use like the kinematics of the globular clusters.
Actually, just the numbers here.
Oh, I see. Oh, forget. Yeah, that makes sense. Actually, I was thinking about the scaling relation between the number of globular clusters and the stellar mass, but it's actually with the total mass of the galaxy. Yeah, you're right. Okay.
Yes.
Perfect. That makes sense. Thank you so much.
Okay. Thank you for the question.
Do we have more questions? Okay, I have a question about the slide. So the error bars here, they're very big for the red ones, but I don't see any error bars for the blue circles and the yellow triangles.
Yeah, we didn't.
So
yeah,
is it because there are no error bars, or the error bars are so tiny?
We didn't get them from the literature.
Okay, so there are, but it's not
yeah.
clear what they are.
We didn't.
Okay, thanks. Is it
But this
just
one is certainly off. Yeah, this one is the one that is completely off because this is highly contaminated.
and there are also these two, I don't know if it's just my monitor, but they're okay. No, I think, is there
So
like
this is for coma, the blue ones, and this is for fornax. So there's
and
some
then you have like
difference
two
in environment.
ones,
Sorry.
like with a different color around magnitude -15.
No,
there-
I think they're just on top of each other by
Okay.
chance.
Larissa, excuse me. Actually, the blue and the yellow ones are very spread around all the graphics. So if you are going to put arrow bars, you just, from my point of view, just in the yellow point that is in the highest nearby NGC 30. Okay, but the other ones you don't need because it's spread around. So
Okay, yes.
it's in the whole domain.
It's like an error bar in itself.
Yes, right.
Okay.
Yes.
Guilherme, go ahead.
Okay, so it's me again. Now that I think about it, is there any hope for us to use the integrated light to check if these extragalactic globular clusters they have multiple populations, or is that like quite of a
Yes.
long shot?
Yes. So there is one more for actually NGC 1316 that has intermediate age. It's a merger remnant in fornax, and there's integrated spectra, and there are claims that you can detect some differences in the populations. But yeah, there are studies in this front, but not many.
I see. Okay, thank you.
Okay, so we see no questions in the chat, nor on YouTube. Do we have any more final questions here? Okay, so as Anna said, you can contact her on email, on Slack. Also, I think you're on our Slack channel, the Linea.
Yeah.
Okay. So if there are no more questions, sorry.
I think I'm in the LSST one. No, but am I not in the Linea one? But I can enter.
Okay. So if there are no more questions, we'll wrap this up. The presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Santos. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar. Thank you.
Thank you.